Okay. Good morning, everyone. My name is Gonzalo. I am an experimental physicist working at Sapienza University of Rome. First of all, I would like to thank the organizers and the reviewers for the opportunity to present this work. Well, which is mainly founded by Sapienza University, the International Institute of Physics in Brazil, the John Templeton Foundation in the States, and the Quantum Lab. So, well, the people involved in this work are two PhD students, Davide Poderini and Iris Agresti, and two professors. The first one is Professor Rafael Chavez from Brazil. He is a theoretician working with us, and Professor Fabio Sciorino from the University of Rome. So, well, I'm going to start with a little motivation about this work, since this is mainly focused on the instrumental inequality. Well, the instrumental causal structure is this one. So we have one hidden variable and two nodes with the outputs A and B, which are connected by the arrows that represent the causal relations, and we have an instrument X. So by changing the parameter X, we can obtain information about the causal relations of the parameters involved. Well, the instrumental variables were originally invented to estimate parameters in econometric models, and nowadays they are taking also space in other fields such as genetics, social studies, networks, and so on. Judea Pearl was the first person that established an inequality for the instrumental variables. So he found the first inequality, and then this inequality was extended by Bonnet. Well, the first violation of this inequality was also performed at the Sapienza University. We perform an experiment where we implement this causal structure, and we exploit photons to demonstrate that this causal structure is not respected by quantum mechanics. And after this work, many other works, these are just 4 of them, show up, and they prove that there is also a connection between the Bell inequality and the instrumental inequality, which is something very important, since there are a lot of things that you can do with the Bell test, such as generation of quantum random numbers, protection of data, and fundamental tests. And actually, also, we were also able to perform an experiment to generate quantum random numbers by exploiting this causal structure. Well, so I'm going to start with the simplest quantum experiment. So you are an experimenter, you have your laboratory with the hidden variables, and you have the outcomes. So by choosing different measurements, you can obtain a probability distribution for your result. And in this way, you can obtain the full picture of your system. When you go with the language of quantum mechanics, at the end, what you have is that the system is a vector living in a complex Hilbert space, and the measurement that you can perform corresponds to the set of orthogonal projections also living in a Hilbert space. So at the end, the probability of obtaining A given X is given in this way by the Born's rule. So the question is, can we use causal modeling to describe quantum experiments? Well, the answer is no, because well, causal models imply Markov conditions on the probability distributions, which are not respected by quantum mechanics. And when they are, I mean, you cannot just witness the quantum phenomena. Well, since, as I told you before, the paper and also this presentation is going to be focused on the instrumental inequality, I have to talk a little bit more about this. So when you are considering that the nodes X, A, and B have 2 possible values, you are working in the framework of Pearl's inequality. So X could be 0 or 1, A could be 0 or 1, and the same for B. And in that case, the inequality of Pearl stands. So the maximum value that you can obtain with the classical models is equal to 1. But what happens when you allow to the variable X, for instance, to take more than 2 values? If you allow X to be 0, 1, or 2, for instance, while A and B can be 0 or 1, you can go to the Bonnet inequalities, which are this one represented by the equation over there. So what you have is that the classical bound is equal to 2, but quantum mechanics predicts a higher value. So the article that I showed you before with the experiment that we performed was actually the violation of this inequality, when the parameter X can take 3 values and parameter A and B are fixed with 2. We did this with a feed-forward experiment, so at the end the arrow that connects A and B was physically implemented. So we don't need to go with a post-selection of the data in order to prove this result. The Markov decomposition of this causal structure is given over there also. So what you have is that the parameter A depends only of X and lambda, while B depends on A and lambda, and there is no direct dependence between X and B. Well, the idea of the presentation and the work itself is to show you that we can exploit exclusivity relations in order to prove that we can obtain information about the boundaries, the classical boundaries and also the quantum boundaries. So the exclusivity graphs are a technique mostly used in fundamental physics, in non-contextual theory, to prove some boundaries and some results. And we applied these exclusivity relations to the causal model of the instrumental inequality and also to the Bell inequality, but they are not just limited to this. You can exploit this to any causal structure with some conditions. But, well, what I mean with exclusivity relations is the fact that in a single round of your experiment, you will have 2 events, and these events cannot happen at the same time, so they are exclusive in this way. Well, as I told you before, the model that I'm going to show you is not just limited to the instrumental or the Bell theorem, but you can exploit different. The condition is that you have only one hidden variable, and you can have many instruments and many variables A and B as you desire. Well, the exclusivity graph is something like this. So you have a big square. Any blue circle is any node is an event. And since this is an exclusivity graph, the fact that they are connected means that could happen the first one or the second one. I mean, if they are connected, you have to choose. For this exclusivity graph is a representation of the Bell inequality. So you have one hidden variable, you have the 2 outcomes A and B, and you have the measurement settings X and Y. If all these values can take two numbers, let's say 0 or 1, you have all this probability distribution. So you have A, B, and X, Y. So you have 0, 0, given 0, 0, and so forth. So in this case, you can establish and you can obtain information just by looking at this graph. For instance, the first information that you can obtain is the independence number. If I decide to take the green points with the probability distribution that corresponds in that case, you can have this second graph, so the one over there, the octagon. So the first information that you are interested in is if there is a classical bound. So the classical bound exists, and how can you obtain it is just by assigning a value of the probability distribution with the deterministic strategies. For instance, if you go to the value, to the first event, 0, 0, given 0, 0, if you assign 1 to that event, you cannot assign 1 to the events that are connected by a line with that node. So the 2 events which are, I'm going here. So this is 0. If this is 1, you cannot assign 1 to this or to this because they are connected. But you can assign 1 to this one because it's not connected to this one. So you can assign 1 to this, not to this one because it's connected to this one, not to this one because it's connected to this one, but to this one. So at the end, you can have an independent number equal to 3, which corresponds to the classical bound with the deterministic strategies. The idea is to understand if we can obtain also quantum bound to this by looking at this graph. So, well, we know that in general, the classical boundaries are contained within the quantum boundaries. And well, in the case that they are equal means that there is no gap between them, and that happens for perfect graphs. So there is a theorem called strong perfect graph theorem that says that if you are able to find within the graph a subgraph with nodes, with cycles or anticycles higher or equal than 5, that means that your graph is not perfect, so allows for a gap between the classical bound and the quantum bound. So this is kind of interesting. And we are going to apply to the same example that I showed you before. So I'm going to choose the green point of the first graph as a subgraph. And as you can see, I can obtain a pentagon. So in this case, I can see that this is a minimum number of the theorem that show me that the graph is not perfect, so I can obtain information about the violation. So the first one is that I can obtain the value of the independence number just by looking at the graph. These graphs are really easy, but when you are working with more complex causal structures, you will need an algorithm. So in this case, the independence number is 2, and you can obtain it just by applying 5 over the first formula. So you have 5 minus 1, 4 over 2, 2. So that's the classical bound. The theta one is corresponds to the almost quantum bound, which is not the real quantum bound. It's a little bit higher. And in this case, corresponds to the square root of 5. Okay, so at the end, just by looking at the graph, we were able to obtain information about the system. You found also the classical bound and the quantum bound. What happened for the instrumental exclusivity graph? So we have 4 pictures here. The first one corresponds to the case where x can take just 2 values, 0 or 1, while the others correspond to x equal to 3 values, 4 values, and 5 values. In all these graphs, m and n are fixed to 2 values. So you can imagine that if you are working with more complex, let's say, values or system, this graph exploits. So it becomes really, really hard just look at this and obtain information. So you will need an algorithm. In the first graph, you can observe that there is no subgraph where you can obtain more than 5 cycles or anticycles. So the graph is perfect and actually corresponds to the Pearl's inequality. So there is no gap between classical and quantum phenomena. While in second, third, and fourth, you can obtain a subgraph. For instance, in the case of L equal 4, so the instrument can take 4 different values, you can observe a pentagon, which is the easiest one, and correspond to the points colored by green. The probability distribution in this case is given over there, and you have that the classical bound is equal to 2, and you obtain the almost quantum bound equal to square root of 5. Okay, so what happened when you increase the values L, M, and N? Well, in this case, you know that your graph becomes really hard, but you can obtain new results. For instance, the first 7 cycles appear for the case 433. That means that x can take 4 different values, while A and B can take 3 different values. And the probability distribution is that one of the equation, where the classical bound is equal to 3, and almost quantum bound is equal to 3.31, which is a little bit higher of the real quantum bound, as I told you before. And the real quantum bound can be obtained with mathematical techniques, such as the NPA hierarchy. And in this case, at the second order, correspond to 3.29. Well, as a conclusion, we have shown that it's possible to exploit the graph approach to extend the study of certain kind of causal structures. We have proposed a formalism to analyze classical and quantum correlations, and this technique reduces the bridge between the quantum information and the causal inference. There are some open questions. For instance, is it possible to extend this technique to other kind of DAGs? Or there are better ways, besides looking for the cycles or anticycles, to find candidate inequalities? We are working on this in this moment. So, thank you.